Guys, the next topic in chapter 4 or module 4 is the naming of ionic compound, naming ionic compounds. Well, it turns on that when we name ionic compound, we start with the metal first. So you start with the metal naming first. Start with metal first. The non-metal will be adjusted so that it will end up with IDE. Then end with the non-metal so I'll say adjusted plus IDE. For example, if you look at in front of you here, the periodic table, we have plenty of metals, as I said, over 70% of the periodic table is metals. So take up something looks like, so we have barium in the second group, plus 2, and chlorine atom is in the 7th group, we'll have -1. Remember, we talked about the octet rule. They like to be close to the noble gas configuration. So the group number 7 is -1. Group plus 2 to A is plus 2. So this is barium and this is chlorine. So how we can write the formula? Did we discuss the writing the formulas of ionic compound? No? Okay. We'll name them first and then we'll try how to put them together. So this is, okay, the 2 of the metal will come to the underneath the chlorine atom, and the one understood nitrogen will come here. So it's like this. But understood nitrogen is, we can just take the one out, it's understood nitrogen. So therefore, and we name this is as first start with the metal. The metal name is barium. And the second non-metal, you end up with chlorine. Not barium chlorine, but we will adjust it a little bit. So we'll end it all this, INE at the end out. We add to it IDE. So barium what? Chloride. Barium what? Chloride. So this will be done, the name of it is barium chloride, correct? The periodic table, and I think somewhere I put in the iCollege for you guys. Let me take this one here first out here. Hold on. Everybody has this? Everybody has this? No. Everybody has this? Okay, let's take a snapshot of it and move on. Let's take a snapshot of it and move on. Okay, guys, so let's take a snapshot of it and take. So I'm taking it out. So everybody by now has this. Take it out. So now let's look at the folder area. That's what your all information in the folder area. The bottom of the announcement section is your what? Is your folder. This is called folder area or course content browser or whatever home. But this is what's your all information about the classes here. So if I click the PowerPoint here, any chapter I can go there. So chapter 4. So I put for you the common ionic charges in a compound. So if I take this one out, make it bigger, yes. So I want everyone will take the quiz number 2. You have to have this one ready. You have to have this printed out and in front of you so you can understand about this charges. So all the metal you can see, and you can see the naming for this. This is very important because you have to have the feeling of those. It will not be complex, but at least you have 1A, 2A, 1A, all 1A's plus 1, 2A plus 2, 3A is plus 3. However, it might be different charges within, but the majority of them plus 3. Majority of them plus 3, correct? But there are some multiple charges, correct, like the Ti, but majority of them plus charges. So the boron is not applicable. The boron is a metalloid, so it can switch plus 3 or minus 3. So anyway, so this table here, periodic table with charges, it has to be printed out and put aside whenever you take the quiz number 2 and exam number 2. So I'm just telling you. So then we switch to the non-metal from here. Not really this one's inert. This one is 8A, 8A noble gas. 8A has charge of 0. So this one is minus 3, oxygen group minus 2, and the fluoride group minus 2. Minus 1, sorry, minus 1. Minus 1. So that's barium is in the 2A, barium is here. So it will be plus 2, and the chloride, the chlorine atoms here, minus 1. So you swap those together, barium is 2A, so it will have 2 positive charges. The chloride ion is in group number 7, minus 1. The ones understood, we don't write the 1, just 1 minus, like this, correct? So, or you can write it if you want, but we don't write minus. So when I make a ionic compound, I have to swap those. It will be barium, and the 2 will be given to the chloride underneath. So we know these 2 coming from the barium. The one here understood, they will come to barium. The barium's like this. This come from the chlorine. So when I write this one here, will be BaCl2. We don't write the 2 here. The one here, we don't write it. It's understood, not written. So called barium chloride. Okay. So this is without charge. How about if we have? Can I take so now? Everybody has it. Everybody has it. Okay. Everybody has it. Yes. No. Yes. Okay. So let's take this one out, and let's minimize this. So you need really this to be printed out for the next quiz. So make yourself a note that you need this. So this chart out. So let's look here. What will happen if we have an element that has multiple charges? So this element multiple charges, like I have lead, correct? This time we'll take lead and N. Well, and then we have lead and N. So lead is write it. I mean, I want just to let you know. You tell me what's the charges on this. This is 3. This is 2. Okay. This is 3. This is 4. what we call this here. It turns out since lead does have multiple charges, so the 2 here is coming from where? From the lead, and the 4 came from the lead. So we have to introduce, anytime I have an element that has multiple charges, I have to introduce a Roman number. So that will be lead, and then the 2 is here, and this is N, nitrogen, adjusted will be nitride. At the end has to be IDE. The other one is lead, but this one is 4 nitride. Everybody knows how the Roman numbers. Okay, everybody knows. So this is 1, this is 2, this is 3. Now when it comes to 4, we have to watch. When it comes to 4, we have to watch. This is 5. So let me come here. When it comes to 4, we have to watch. This is 5, correct? 4 is 5 minus 1. The left, if you go left, that's minus 1. Go to the right, plus 1. So I'll say this is 4. This is 5 minus 1. This is 4. Now what about, this is 5. How about 6? 5 plus 1. 6. Right? So this is 6, 5, 4, 3, 2, 1. We'll go for up to the deca number, up to 10. So that's a 6. 7 will be, that's a 7. 8 will be, always up to the 4, then you have to watch. The 4 you have to watch. And all the 4 steps. 8, then the 9 you have to watch. 9 is, this is 10. Correct? In the left, minus what? This is 9. This is 10. This is 1. In the left, 9, 10 minus 1 is 9. This is what? 10. So how about if I have 32? I want to write 32 in Roman numbers. Somebody will tell me. Everybody knows. How many is the tens we have of the 33? Correct? 1, 2, 3. How many we have? 2. That's in the positive sense, correct? So that's a 32. Everybody got that now? Everybody knows how to do it, correct? Okay, good. So that's about the Roman number. We'll not go for this, but at least you get the idea of how to write those Roman number. We'll go for up to maybe, we don't go even 9 or 8, but at least you will know how to do those. So let's get another example. How about if I have iron, and then I have sulfide, and iron and sulfur, and I have sulfur. So the iron I have here, the charges, if you look at charge, it has 2 and 3. Iron has 2 multiple charges. So we'll have 3 plus. And the sulfur is group number 6A. It's 2 minus, and this is 2 minus. So when we combine those together, we have to swap. The 2 of iron will come underneath the sulfur, and the 2 from the sulfur will go underneath the iron. Well, nature will not support this type of molecules. It has always divided by the common number, which of 2. So this one will be FeS. Correct? So how about the other one? The other one is very obvious. Iron will have the 2 from the sulfur, and the sulfide will have the 3 from the iron. So we don't have a common number, so we'll keep them as they are. Everybody's following? Now we name this one here will be iron, and then you look here, this is coming from the iron itself. So this is iron 2 sulfide. That's all of it one word, by the way, all of it one word. And with this one here will be iron. What's the charges here? The 3 is coming from the iron. Iron 3 sulfide, one word. All of it's one word. Okay, guys? Who's following? So that's the ionic compound with multiple charges. We add this Roman number. So, but sometimes we have polyionic atoms. Polyionic atoms that multiple non-metals will come and combine, and then they give themselves certain specific names. Can I take this one out? That's it. You can take snapshot if you want to, or you can review the lecture afterwards. So, can I take it out? Okay, let's take it out. Let's have the now we said back to this. We have another one to take care of it. This is another one you have to print out. You have no other choice. You have to print this one out. Okay, guys? This one here, the polyatomic ions. Polyatomic ions are non-metals are combining themselves in a way that it's in a way they have certain amount or certain specific chemical reaction and physical reaction as well. So those polyatomic ions will come and combine themselves with the metal, and naming them will be as such, will be whatever the name of the metal. All of those polyatomic ions are negative. If you look at this here, all of them are except one polyatomic ion is all those here, polyatomic ion here. And there are many. This is just few. There are too many. I mean, way too many. Okay, guys? The only positive one is this one here. This is positive, the only one, positive polyatomic ion. Means it came from NH4. 4 hydrogen atom non-metals and 1 nitrogen atom. There's 5 non-metal atoms. 5 non-metal atoms. That's polyatomic. And this is iron, and it is positive. All the other ones you can see are negative. And the way I learned those long time ago, I have to write the name of this polyatomic ion and the formula of it with the charge. With what? With the charge. Because this way I can understand. I write like such a table 10 times, 20 times, so I can memorize their name and their charge. But for the time being, you should just print this one out, keep it with the previous one, the multiple charges periodic table aside, because that will come to name those compounds. And let's look how we name polyatomic ions. Okay, so always ionic compound naming is the most difficult part of all. Can I take this one out? Can I take this one out? Okay, so let's take one of those here, and any one of preference of those you like, any one of those groups you like. Which one? Anyone? That their names is here. Their names are here. Anyone? What's that? No, that's oxalate are here. Oxalate is C2O4 2 minus. And yeah, those are here, and they are separated by this line. Okay, guys, which one? Bromine, bromate. Okay, bromate, BrO3 1 minus. So you have to bring this one out because without this it will be lost. You will not know the name of this polyatomic ion. So can I take this one out? So let's look up bromate then. Okay, so take this one out. I'm minimizing this. Okay, guys, I'm minimizing this here. Minimizing iColish. And let's put bromate. So we'll start with the smaller one, and then we'll start the complex one of the Roman number, correct? Because that's ionic compound. We are looking at the ionic compound. So let's look at the ionic compound here. I have bromate, correct? Bromate is BrO3 1 minus. 1 is understood, always not written. And then I can take out of the bromate here. Suppose I have aluminum. Aluminum in 3A has 3 positive charges. Okay. This one here, understood, not written. Minus 1 minus. The 1 always understood, not written. We don't write the 1. Please, we don't rewrite 1. Okay, guys? So, what will be this combination of those one element, metal, and then with this polyatomic ion? Well, it turns out to be, I have to put brackets or parentheses, Al, and then the whole polyatomic ion in parentheses, and the 3 here will come all the way at the subscript of this, correct? And the 1 here will come as 1. Well, the 1 is understood, not written. We'll just write it Al BrO3 3. And the name of it will be aluminum bromate. Okay, guys. Somebody took oxalate. Let's take oxalate and see what will happen to that. So, aluminum bromate. One word. So, aluminum bromate. So now, let's take another example with some Roman number. Can I take this one out? Everybody has it? Everybody has it? Okay, good. So let me take it out. So now let's take something is with the Roman number. So we'll take copper comes with copper plus 1, understood, not written. I mean, I can write, whenever I write 1 plus, 1 negative, that means always there is 1, correct? And then I will take a polyatomic ion that's called oxalate. And oxalate is always -2, correct? Then we have copper multiple charge. It has 2 plus, and the oxalate is 2 minus. So copper comes, that's copper. Copper comes in 2 multiple charges, plus 1 plus 2. And this is polyatomic ion 2 minus, correct? So in order to get this one here done, you swap, the 1 will come here underneath, correct? So that will be copper, and then you can take the parentheses under 1, correct? And the copper itself, copper is 1, and the copper itself will have, copper will have 2, that's copper here, copper 2. So the 2 will come underneath the copper, and the 1 will come underneath the whole thing. Now, since we have 1, so no need for the 1 here. So I can write it copper 2 and then C2O4. So understood when I write this one here, this way it means this here. But we don't write, we save ourselves the parentheses and the subscript one. So understood, not written. And the name of it will be copper 1 oxalate. Copper 1 oxalate. Now how about this one here? The copper will have the 2 from the oxalate, and the oxalate will have parentheses now 2 from copper. Does nature support this common factor? No, except for hydrogen peroxide. Yes, but this is nature does not support this. So that will be what? That will be copper oxalate. No need for, because it's 1 to 1. So the 1 here, 2, that's a common factor of 2. So you can write it just copper 1 oxalate 1. And the ones understood, not written. So that will be the name of it will be then. The name will be copper 2 oxalate. Copper 2 oxalate. Are this following? Okay, so that will conclude the naming of the ionic compound with the metals that has only one charge, or with the metal they have multiple charges, correct? So, and we know that we can have combination of those metals with multiple, with a polyatomic ion, and then we have to observe this, the naming of those polyatomic ions, okay, from the chart. So, can I take this one out? Can I take this one out? Well, then the next one here is how to name the covalent compound. The covalent compound is, as we mentioned, is a combination with nonmetals together, correct? Combinations of 2 or more non-metals. Okay, so we combine nonmetals together to get this covalent compound. There is no transfer of electrons from the metal. They are sharing those nonmetals share their valence electrons. Okay, for example, I have HCl. HCl, correct, guys? H, the hydrogen has 1. We'll come after this topic, we'll go to lose that structure. Hydrogen group 1A has 1 valence electron, is 1. The valence electron is number of the group. So 1A, this is 1A. So 1 is, this here is 1. Combine itself with 7, 4, 5, 6, 7. This is 7A. Those of valence will be 7A. So there is no ions there, but we'll look into this one here. So what's happened is this 2 nonmetals will come and combine themselves by sharing what? Single bond. They are sharing their valence electrons. So those 2 electrons are belonging at the same time to the chlorine atom, at the same time to hydrogen. They are sharing this nonmetals. So This is the covalent compound. The covalent compound is a combination of nonmetals, and in this combination, each atom will share its valence electrons. There is no transfer of electrons, so there is no transfer here, loses, and then electron will come like this, plus, and then minus. They are not really like this 100%. No. This partial, yes, partial of. We'll know later on about the partial, So this is this. It's not happening like this way. So they share their valence electrons within among themselves. Now, how we name this covalent compound? Can I take this one out? Everybody has it? Everybody has it? Okay. Let's take it out, and let's before we have to again, the same like Roman number with the metals with the multiple charges. We have here issue with the Latin number, or this Greek on Latin. So we have one. I will go up to 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 1 is called mono, 2 di, 3 is tri, tetra is 4, 5 is penta. Oops, sorry. Tetra, penta. How about 6? Hexa. How about 7? Hepta. How about 8? Octa. How about 9? Nona. How about 10? Deca. Okay, deca. That's the name of deca. Means what? Means 10. Deca means 10. Not deca, student deca, but deca is 10. This is a Greek numbering. So, okay, guys. So, we have, in order to name these covalent compounds, we have to know these numbers. So I did not put them in a chart, but please take a note of this. They are not in the chart, but in the naming we learned them. So everybody has them? Everybody has them? Take them down. Okay, so now let's look at one of the examples, just simple one. I have, oops, sorry. Now we are looking at covalent compounds, correct? No metals. So we have this one here, we want to name, and then we have this one here, and this one here, and this one here. Well, how we name the first one? Well, you start always with the first non-metal. The same thing we started with the ionic with the metal. The first thing in the ionic compound is the metal, correct? And we write it as such. So the first thing in a covalent bond is we name it after the non-metal. So it will be standalone naming. So this will be nitrogen, correct? And we know we have too many oxygen there with different numbers. So this is understood, not written, is 1, correct? But it's understood, not written. We don't write it. So this is nitrogen and mono oxide, correct? Now this is too much. You say nitrogen, mono, and then pause, and then oxide. When we have these two vowels, that's two. So we take the mono out. So nitrogen monoxide. Okay, guys? Nitrogen what? Monoxide. Otherwise, it will be very, very difficult to pronounce because you have to make a pause. Nitrogen mono, pause, and then oxide. No. Nitrogen monoxide. Just one word. Okay? So This one will be nitrogen what? Somebody will tell me? Dioxide. You see, we don't have to pause in between. So there is, although we have two vowels, we are not doing this. However, the vowel, you know, O and A, it's always a problem. You know, we have five vowels, correct? So, which beside this one here? E, which other one? U and I. So, those two O and A vowels, so we have to watch that whenever we have them there, we have to eliminate them to make the pronunciation is smooth without like we are hesitating when you are saying nitrogen, oh no, and then you pause for a few seconds and then outside. That's like you are hesitating, you are not in one, talking one word. So, how about the other one? Now we have to watch. We have what here? Two, correct? So that will be dinitrogen, correct? Means two nitrogens. And this is what? Trioxide. All of it one word. All of it one word. Okay, guys? So how about the next one? Dinitrogen. Now we have a problem. Pentar and then pause. Now that's even the sound of it is very funny, correct? It sounds very funny too. Then we have to get rid of the vowel here, the vowel of the number. So pentoxide. So always remember this whenever you have two these vowels, you have to get rid of them because just to make the pronunciation. So now let's take another one. Can I take this one out? Everybody has it? Everybody has it? Okay, take it out. Okay. Let's take one here and then you tell me how to name those here. All those are real compounds. All those are real compounds. It's not really. So, what's the name of the first one? What's the name of the first one? Correct? Two. Diphosphorus. And what? Trioxide. One word. There's no problem with the vowels here. Okay? How about the other one? Phosphorus. Pentoxide or pentoxide? Pentoxide. So no A. So pentoxide. We got rid of the A now. We are very professional. How about this one here? 4. Remember what will be that? Tetra phosphorus deca oxide. No, that sounds very funny too. So will be what? Dec oxide. One word. No A. Okay, guys. That's all. The covalent bonding or compounds naming is the easiest one. It's the easiest one. Always the problem with the metal, the ionic compound is the difficult one because they have Roman numbers, they have multiple charges, and you have to look at the polyatomic ions. And we'll go back and look at the ionic, the polyatomic ion. Can we are okay with this? Everybody knows how to name those, okay? So let's take polyatomic ion and you tell me, correct? So we have acids, for example. So remember this acid starts with hydrogen, correct? And those are the polyatomic groups or ions, polyatomic ions or groups. So it turns out to name those compounds, you have really to know this polyatomic ions. So this one here is called one word, perchlorate. Perchlorate. Per, and this one here, one negative. All of those are one negative. This one here called chlorate. And this one here called chlorite. ITE. This is ATE, ATE, this ITE. That's the anion itself. Now, if this is ClO, will be one negative. Hypo, I have to write it here. Hypochlorite. Now, if you combine them in a compound, correct? In a compound with a metal or whatever. So, suppose I want to put them in a metal. So let's take the hydrogen out and put them in a metal. So and then we'll do the acid later on. So let's put they are combining themselves with sodium, sodium, sodium. So sodium is +1, and those all -1. So will be no charges. So something like this. So what will be this one here? Sodium what? Sodium what? Chlorate, correct? Not chlorate, perchlorate. So sodium per. This is sodium what? Chlorate. This is sodium chloride. And this is sodium hypochlorite. Okay, guys. Everybody has it? Everybody has it? Okay, so now I want to add the acid, how we name the acid. See, the naming will be a little bit different. So name the acid. So can I take everything? You have everything here? Okay, let's take the naming here. Let's take this one out here. Okay, let's take sodium out too, and then put the acid. Now, if you put the acid there, look, if you put the acid, then the acid always named with the first, its name, which hydrogen, will be hydrochloric. Not really hydro. This one, because of polyatomic, if this binary 2 will be hydro. This is will be not a hydro. We take the standard first. We have to determine what's the standard acid. This is our standard. And this is called the acid with the polyatomic. We said chloric, from chlorine, chloric acid. This one is hyper, so hyper. Hyper means more or higher because it has higher oxygen, one oxygen more, correct? So hyper means higher. So then we have to take just the HY out, and then we say this is what? Perchloric acid. So this one here is, let me write it so you can follow it here. So this one here is perchloric acid. Always remember ic acid at the end, acid here. Ic acid at the end. So this one here is less one oxygen than the standard, will be given chlorous, OUS, chlorous acid. And this one here less than the chlorous will be hypochlorous acid. Okay, this one here is chlorous acid. So this is the naming of those polyatomic ions as acid, different when they are as in the ionic compound. Those acids are all covalent compounds. Any question about this? Any question about this? Well, if you have no question, then we'll go for the next. Can I take them out? They has them? They has them? Okay. We finished this one here. Now we want to see how we combine this one here, those covalent compounds. From now on, the ionic compound is done. All of what we speak from until the end of the chapter is about covalent compound. So the covalent compound, something called can be written in their structure called Lewis dot structure. The Lewis dot structure is presenting the valence electrons of each element as a dot. So representing VEs, valence electrons, as dots. An example here, aluminum in 3A. So aluminum has 3 VEs. So how many? It has 3 VEs. So now I can write aluminum here. Oh, this is 1. This is 3A. So 3A. Let me write it here. 3A, group 3A, group 3A. So I can write the Lewis dot structure of aluminum. Lewis dot structure of aluminum here would be Al, 1, Al here, 1, 1, and 1. So it has how many? 3. So 3 V's. So 3 dots equal 3 V's. Okay, guys. So carbon, let's take sulfur, for example, sulfur in 6A. So let me take this one out. Everybody has it? Everybody has it? Okay, so let's look at sulfur here. Sulfur is group 6A, and number of the group here is number of the valence electron. Number of the group equal number of VEs. So 6A, meaning sulfur has 6 VEs. So I can write sulfur here, and then I have to write one here, 2, one here, one here. It does not matter where, but one here, one here. Those are what? 6. Can I write them like this? S 3, 3, 3, 3. No. Can I write them 3 and 2 and 1 here? No. So we know why is Lewis that structure is controlled by two rules. So let's write those. Let's go through those rules. Why is this one the only one is correct and all the others not correct? So there are two rules controlling the way those valence electrons are represented as dots on the element. So can I take this one out? Everybody has them? Everybody has them? Everybody? No? Yes? Okay, so let's take those two rules and then talk about those two rules. The two rules are controlling the V. Yes. Controlling the appearance of the controlling the appearance of VE dots. Well, the first one called Pauli exclusion principle. The first rule here. First rule called Pauli exclusion rule or principle. So this Pauli is telling us that each orbital has to have maximum of 2 valence electrons. So each orbital can be filled by a max of 2 V's. Okay? This is number 1. Number 2, they have to be filled with opposite spin. The opposite, when they spin differently. So they have totally opposite spin. Spin means rotation around the nucleus. Around what? Around the nucleus. Okay, guys, so let's look at this. That's the reason we can't write more than 2 in each orbital, more than 2 in each what? In each orbital. Did we go through the orbital diagram, orbital? Yes, I think we did. Correct? orbital diagram in the first quiz, I think. Yes. Yeah, so whenever I write any box, for example, let's just remember this one here. I want to put electron configuration of chlorine, for example, chlorine. Okay. Now, in electron configuration of chlorine, we have three types. But I would like to type this one here is orbital diagram. So the orbital diagram will tell us, according to Pauli here, first of all, you have to go, I will go all the way, chlorine is in the third period. I go all the way to the end of the third period. I go where up one will be neon, correct? And it is in the third period will be 3s2, 3b5. The valence electron has to be equal number of the group, which is 2 plus 5 is Be is equal to 7, because this chlorine is what? Group 7A. So it should have 7, correct? Now, if I look at this chlorine electron configuration and put it there, you will see that each of those has to be occupied with one dot or one arrow. So can I take this one out? Everybody has it? Everybody has it? Okay, let's take it out. So if I put the electron configuration of chlorine, this is orbital diagram. Then I have neon, that's 10, 3s2, 3p, 3b, not 6, 5, sorry. So that will be neon, 3s, and p is always divided into 3 boxes. So what is telling us that Paul is telling us that this is 3s here. One arrow up, the other arrow down, correct? And maximum of how many? Maximum how many? 2 VEs here, correct? And they have different spin. And the second rule we'll talk about it. It has to be going singly and parallel to each other. They have the same orientation. So that's 3. We have 2 more because that's 5. One is here down, one is here down. You see, in each orbital or suborbitals, you have maximum of 2 electrons. You don't exceed the 2 electrons, correct? So that's what it's saying. It's saying maximum of 2, and second rule of Pauli, they have opposite spin, opposite. One is counterclockwise, one clockwise. Okay, guys? So this is one. Now the second rule here, called Hund's rule. Hund's rule will tell us that the electrons will go single, one electron at a time, and they have parallel to each other. So if I have neon here, they go single. First start with 1, that's 3s2, correct? So, and remember, this is 10 electrons here, so it makes 17, correct? So, one is up, singly up by itself. Then the second one will go down. And you can see it in the second orbital. You have 3 here, So when you enter them inside, first they enter singly and parallel to each other, means they have the same spin. So up, 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 correct? And then down, down. So let's put the Hund's rule here. Hund's rule tell us that the let's write it here. Hund's rule: electrons or the VEs enter the orbital or suborbitals, enter the orbital or even suborbitals, singly. Number one. Number two, parallel to each other, parallel to each other. Okay, guys. So that's how we can visualize that structure is coming from, controlled by this fact. You cannot write two more than two in the orbital, two dots in one orbital. So let's take this one out. Can I take it out? We have still plenty of time. That's good. Let's take it out. If now look at lose that structure, and if I wanted to do we have a lose that structure just only for covalent compound? No, we have for covalent compound as well as for ionic compound. Let's do covalent compound that has a multiple of not multiple, but a metal is totally different. Let's put, correct, if I have a compound looking like lose that structure, it can be getting very complex if we put all those are together, correct? So I want to look at the later on we'll see some compounds like POCl3. So this compound here, phosphine, or call the commercial name of it, but look at this. How in the world I will know to start those type of compound? This is very complex. Let's take the smaller one and then take the complex one. This one here and those one here. Those the smallest one, the easy one. What is that structure of this? Let's start the easy one or take the difficult one, correct? So when it comes to this one here, I mean, I have two hydrogens. The Lewis dot structure has rules, and one of the rules is you have the let's write the rules here. Rules of Lewis dot structure. Okay, so first of all, you start with the element that's least electronegative in general. We'll talk about electronegativity there. So most of the time, not always, most of the time, the least electronegative atom okay, the least one is kept at the center of the compound or molecule, center of compound or molecule. Okay, guys. Number 2, I took this one. I should have written. And if you look at this, number 2, we can the most electronegative atoms always mostly kept at the edge, not in the center. So when I say this, let's take those examples here. Let's take those examples. We'll come back to them. Let's take them out. Sorry about this here. Let's concentrate on the rule and then we'll come back to this. So this is the first rule, correct? Lewis dot structure. So this is the first rule. The second rule here is most electronegative. We'll talk about electronegativity later on. Atom is kept at the edge, and the edge sometimes called terminal of molecule. So most electronegative are kept at the edge. Number 3, hydrogen is always kept at the edge. Hydrogen is kept at the edge. Okay, guys. Number 4, number 3, hydrogen is kept at the edge. Number 4, 4 elements should observe octet rule, correct? 4 elements: carbon, nitrogen, oxygen, fluorine should obey octet rule. We talked about the octet rule. So they have to have 8 to mimic the configuration of noble gas. So elements have to have 8 VEs, like noble gas. Okay, guys, see enough. Those are, we are looking at them if they are really obeying the octet rule to have 8 or not. So let's go back to our examples. Can I take this one out? Now with this in hand, we can look at that. Can I take this one out? Okay, so let's see here. We have still four minutes, guys. So let's do the simple one. Hydrogen, oxygen. We know this oxygen later on. You'll know that's most electronegative, and hydrogen, as always, at the edge. You cannot put it in the center. So I'll put here oxygen. I'll put here hydrogen, and here is hydrogen. Now let's put the valence electrons here. 1 valence electron, 1A, group 1A. 6A, oxygen 6A, it has what? 6. So I put 2 here, 4, and 1 here, and 1 here. I have to have what? 2 maximum in 1 orbital. I cannot have 3. So then I will start here, guys. Connecting single bond. Correct? Hydrogen always at the edge. And this is oxygen, correct? Now if I look at this like this, so look at the whole thing here. Let me just see here. Just hold on. If I look at this is all this. Oxygen is the most electronegative atom and has to be in the edge, but this one is an exception for the rule. This is the Lewis dot structure of what? Of H2O. Now the question is, we have the rule. It says we have carbon, nitrogen, oxygen, and fluorine atom. We have to determine if they have 8 valence electron in combination. Well, let's count. This is 1, 2, correct? 3, 4. Those are unshared, correct? Those the shared one, 5, 6, 7, 8. It does have what? It does have 8. So here it's 1, and here's 1. So it has 8. So therefore, we say this is octet rule is okay. Octet rule is okay, correct? So how about the other one? If I have 2 electronegative atoms, I should not put them, and this is only the exception for the rule. So here's oxygen, oxygen. See, I have my rule tell me always don't put 2 electronegative together. But I have hydrogen here. Hydrogen take priority. It has to be at the edges. So hydrogen will be here. Hydrogen will be here. Then I have here 6 here and 6 here, guys. And hydrogen will come here. Hydrogen will come here. So all in all, the covalent will be, here is covalent bond, here is covalent bond, and here is covalent bond. So this one will be looking H, O, O, H. Okay, guys, and oxygen is as octet rule. You can determine each oxygen has 8. Okay, we'll come back. We'll take the complex one. We'll take the complex one. We'll take the one we have written. So I'm ending the lecture here.